Yeah, my name is Hilary Makando, student number 215078829. And this is the second part of the simulation for the demonstration of the project. Basically, we have the adaptive antenna array designed in Simulink. So on the far left, we have the transmitter, which basically generates a pulse that is required for our signal to be parameterized with the proper values or parameters. The generated signal from the transmitter is then passed through into the channel, and from the channel it goes through the receiver array, where it combines with the interfering angle and the desired angle signals along at the receiver array end. So basically, in this case, we're making use of a 60 degrees direction of arrival. That is what we are choosing as the design of the array. We want our signal to be directed in the direction of 60 degrees. Then as you can see, for the interfering signal, it's directed at 0 degrees. But that does not mean that noise is not simulated within the system. It is simulated. It's only that we are not just specifying the direction of arrival of the interfering signal, basically. Although it is being simulated. We have the next block, which is the direction of arrival and beamforming block. Basically, with this block, along with the receiver array block, is where you specify the parameters of your antenna array. And in this case, we are making use of a uniform linear array, which has 8 antenna elements and just varying the distance between the antenna elements. The reason for the specification or the fixed number of antenna elements is due to the fact that with MATLAB, specifically in Simulink, during the course of my research, I discovered that with the S parameters, or the number of ports, or simply as denoted as the number of antenna elements, it's practically impossible to simulate more than 8 antenna elements with noise in the system. So in this case, basically it's only possible to simulate the number of antenna elements up to 8. That's when you're gonna have noise in the system for it to be simulated. But if you have more than 8 antenna elements or ports, which are categorized as S parameters in Simulink, then noise will not be simulated in the system, which is not what we want. We want noise to be in the system so that it can be simulated and nullified at the same time, along with the desired signal. Then moving on to the next block is the demodulation block, which basically just extracts the signal from the beamform signal basically. So it consists of an AGC, forward AGC, and which basically has parameters such as the power of the AGC and this basically the step size. Then with the next block is the modulation error ratio measurement, whereas this block basically just determines the output error of the array. Then finally is the control logic block, which simply just predicts or determines the direction of arrival angle. So in this case, with this antenna array, we're gonna be making use of, as I specified at the beginning, we'll be making use of 8 antenna elements due to the fact that it's the optimum number of antenna elements you can use with system being with noise being simulated in the system. Then in terms of the inter-element spacing, there will be varying of the inter-element spacing, varying from 0.125 lambda up to a point where we feel like our antenna array output or results have been satisfied according to our the desired output or results. um, within the narrowband receiver array. This is where the operating frequency of the array is specified, and in this case we are making use of an operating frequency of 5 gigahertz for the antenna. And due to the fact that the wavelength, our distance is measured in wavelengths, we have a propagation speed, which basically denotes that the equation of lambda from derived from first principles is being used with a standard value of c being the speed of light, which is 3 times 10 to the power 8 meters per second, is the value used in this case. Okay, and as we open the the dialog box of the operating frequency, just to confirm that it is indeed operating at 5 gigahertz. This is the value which we decided to go along with, due to the fact that I decided to make use of 5 gigahertz, which is most applicable in 4G applications. And with further research, I discovered that with 4G applications, they normally range between an operating frequency of around 3 gigahertz to 5 point something gigahertz. But the 4G applications do not normally exceed 6 gigahertz. With 3G applications, they normally range from around 1.8 gigahertz to around 2 point something gigahertz. So with that being said, we move on to the next section, which is uh, the specification of the uniform linear array parameters. It can be observed here. We have the 8 number of antenna elements and the inter-element spacing, which is 0.5 lambda. We are gonna be varying this inter-element spacing up to a point where we feel like we are achieving what we desired at the beginning of the simulation. Then once the setting up of the uniform linear array parameters has been finalized, then run the simulation and observe the results. From the simulation results obtained, we can now observe the properties of the array on the frequency spectrums. The first frequency spectrum we have here is the one from the transmitter, where an a pulse was generated by the transmitter and passed through the channel into the receiver array, where it was combined with the desired signal angle. Basically, you can see this is the desired signal, and basically the main lobe of the desired signal. Then this frequency spectrum, basically it indicates that the main lobe is currently being disturbed by an interfering lobe, a side lobe on the far left, due to the fact that this frequency spectrum is without beamforming. Then as we move on to the far right, the third figure of the frequency spectrum, we observe now the properties of the effects of beamforming on the output signal of an array. You can see the main lobe right here and interfering signal, which tried to, in the system, it tried to interfere with the main signal, and it was nullified as a result of beamforming, which is a crucial aspect of antenna array. And in terms of the results obtained with power, we can observe that we receive the transmitter, The receiver array basically generated an input power of around 6.672 dBm, and the radiated power was at 1.134 dBm. So essentially, the radiated power received was 3.134 dBm. So in that case, we can observe that the efficiency of our antenna is not that great at the moment, which is approximately just below 50%, and it's far from what we desire to achieve basically. So in that case, we further increase the distance between our antenna elements, essentially. Okay, the next inter-element spacing would be 1.75 lambda. Then once the inter-element spacing has been changed, go back to the simulation and run the simulation and wait for the results of the simulation again. Okay, from our recent set of results, we observe that our efficiency in terms of power input and radiated power has slightly improved from below 50% to around a range of 55%. And we can also observe a ratio change of the direction of arrival, whereas we initiated our signal angle to be at 60 degrees, and the estimated direction of arrival was around 98.21. So in terms of you obtaining the radiation of the array, you basically just take the ratio of the two angles, which is what you use to calculate the directivity of your antenna. And since now the antenna is 55%, but it's not quite what we still want to achieve, because 55% is a basic efficiency ratio of an antenna, and in this case, our antenna is a smart antenna, so it should have a much higher efficiency as compared to a standard normal type of antenna. So to solve to adhere to the issue, we continue with the increment of our antenna, the inter-element spacing between our array element. Okay, once the increment of the inter-element spacing has been increased from 1.75 lambda to 1.85 lambda, we then go ahead and run the simulation again. Then we further observe the results of the simulation. After further increment of the inter-element spacing from 1.75 lambda to 1.85 lambda, we further notice that the radiated power has improved, which gave us an efficiency of around 72%, basically. So now our antenna is practically 72%, theoretically 72% efficient, with an increase of the direction of arrival at 94.65 degrees. Essentially, you take the ratio of the two signals, of the two angles, the one where we injected it with impulse, which was generated at the transmitter, and the one which we get after the control logic. So with that being said, we now further increase the inter-element spacing to a further distance of 1.9 lambda and observe the differences. After further increment of the inter-element spacing to a distance of 1.9 lambda from a distance of 1.85 lambda, we again run the simulation and observe the results. with the latest simulation results, you can observe that the radiated power has improved as a result of an increment of the inter-element spacing between the antenna elements, and the efficiency is observed to be at around 86%, which can still be further improved at increasing the inter-element spacing between the antenna elements to around, let's say, 1.95 lambda. So basically, with this simulation, the main objective of simulation was to basically design, simulate, and model a smart antenna array using MATLAB. And the second one was to determine the efficiency, directivity, and gain of the smart antenna array. So with that being said, the simulation results fully support the theories behind the expected results. And finally, the way this simulation model basically works is almost the same as the MATLAB code simulation, whereas every time you run the simulation, new set of array weights are being generated. But in this case now, in the Simulink simulation, we now have we don't have complex array weights as we did in the MATLAB code simulation. So basically, you can measure the input power, radiated power, and then you can obtain your efficiency from those parameters. Then using the equations presented in the presentations, you can then go on to calculate your directivity. Then finally, the gain is basically the product of your efficiency and the directivity, which gives you the final parameters of the gain basically. So in conclusion, this was the demonstration of the second part of the simulation in Simulink MATLAB. Thank you.